All right, let's talk planetary interiors. So we're going to start with magnetic fields today, which is a product of planetary interiors, and then we're going to talk about the interiors of the different planets and how we know about the interiors of the planet. So let's get started. First of all, planets have magnetic fields. Some of them do, some of them don't. We'll talk about what generates them in a minute, but let's start with the Earth. The Earth has a magnetic field. Earth's magnetic field actually puts uh, magnetic, imaginary magnetic lines that exit the Earth at the North Pole and come back into the Earth at the South Pole. So it acts like a giant bar magnet. And the magnetic field actually shields us from charged particles streaming from the sun. These charged particles streaming from the sun, they're called a solar wind. As the sun produces nuclear fusion, energy via nuclear fusion, it's converting mass to energy. It streams out energy in all wavelengths. As it does this, it blows it out into all directions in space. It also blows out charged particles. When the charged particles hit this magnetic field, they actually get deflected around it. And so we are spared from a lot of the dose of charged particles from the sun. Some of them do actually get caught up in between the magnetic field lines. Those are called radiation belts. Some of the particles in the radiation belt swirl down the magnetic field lines and hit the atmospheric molecules. When they do this, the electrons in the atmospheric molecules get excited for a moment. They are charged up with energy, so they jump to a higher energy level. But that excitement fades, and the electrons jump back down to their original levels. And when they do that, when any time an electron jumps down a level, it releases a color specific to that energy that it's giving off. So if it jumps from level 4 to level 3, that level 4 to 3 is a particular wavelength of energy. And it's usually a visible color on the visible spectrum. When you put all that together, beautiful colors are produced. We call them aurora or aurorae. These beautiful, shimmering, flowing, they're almost ghostly in appearance as they flop around, they kind of like flitter around in the sky, are in beautiful colors. And the colors are produced by the different molecules that are excited depending on the levels in the atmosphere. You see magenta produced by nitrogen in the lower levels, green and blue produced by oxygen and nitrogen in the mid levels, higher levels, deep reds by oxygens. They call them aurora borealis in the north and aurora australis in the south. But these are the beautiful auroras, and this is how it's formed. It's eventually these auroras start from those streaming charged particles from the sun, known as the solar winds. So, how does the Earth get that magnetic field to begin with? Well, two things: it's liquid metallic interior and rapid rotation. Liquid metal, first of all, when any kind of metal has the electrons in a very packed state. The atoms are packed together so much so that their electrons can kind of like flow freely between atoms as long as they kind of keep a stasis or an equilibrium. So copper wire, for example, when electrons flow through it, they kind of go from areas of more electrons to less electrons, and so you get an energy flow, an electricity flow. Um, when this happens in a liquid metallic environment that's rotating, it actually produces a magnetic field. And so the Earth acts like a bar magnet. Other planets have magnetic fields as well. Any layer in the interior of a planet that is liquid metal or acts like liquid metal and it's moving can produce a magnetic field. Jupiter and Saturn are great examples. Jupiter and Saturn are these awesome states of nature. So Jupiter and Saturn are very big planets, lots of hydrogen in their atmosphere. When you get down into the lower levels, the hydrogen gets so super compressed that it becomes a liquid. So you have liquid hydrogen uh, below the atmospheric surface of Saturn and Jupiter. And then there's so much liquid hydrogen that the lower levels of liquid hydrogen are so super compressed by the gravitational uh, weight of the material above it that they get forced into a super compact state where their electrons can flow freely through that liquid hydrogen. So it becomes quote unquote liquid metallic hydrogen. And liquid metallic hydrogen is just like a liquid metal layer. And because Saturn and Jupiter rotate rapidly, boom, magnetic fields. Jupiter has a massive magnetic field. When you look at the other interior planets, Mercury doesn't necessarily have a magnetic field. It kind of has a different magnetic field. We'll talk about that one in a sec. Venus has little or no magnetic field because it's so slow in its rotation. It takes 243 days for Venus to rotate around one time. So whereas it probably has a liquid metal layer, it's not rotating or moving. If Venus's surface was cooler, Venus's surface is super hot. It's hot enough to melt lead. So it's almost as hot on the surface of Venus as it is in the interior of the planet. So there's really not even convection of rock to cause motion. So Venus, not really a magnetic field. Talked about Earth. Mars has a weak magnetic field. It's not very strong because it's cooled off inside. It's a small planet, not very much atmosphere. So all that interior heat is kind of dissipated off into space. Not much of a magnetic field. As I mentioned before, Jupiter's magnetic field is huge. It has a really big liquid metallic hydrogen layer, and it rotates once every 10 hours. That is really fast for a big boy. So millions of amps of electromagnetic field are flowing from Jupiter in these invisible magnetic field lines. The closest moon to Jupiter is called Io, and Io is one of the most volcanically active bodies in the solar system because of Jupiter's gravity. Jupiter's gravity crunches and yanks on Io's surface, frictionally heating it. Lots of volcanoes. These volcanoes erupt, and because they're so close to Jupiter and its magnetic field lines, Jupiter actually picks up Io's volcanic particles and brings them down into Jupiter's atmosphere. And so that enhances the auroras. So if I ask you a question on the quiz, what enhances Jupiter's auroras besides its massive liquid metallic hydrogen layer and its very fast rotation, you would say Io's volcanoes. The resulting aurora are larger than the entire Earth. And Mercury is a special case. Mercury is so close to the sun, like Io being close to Jupiter, Mercury gets yanked on its surface by the sun. And it causes frictional heating inside, causing a partially molten layer, maybe solid or partially liquid. As a result, it's got a little bit of a fluctuating magnetic field. How do we know what's going on interiorly in planets? Well, we're going to talk about that. First of all, looking at what is inside of them first. The terrestrial planets, like Earth, the Terra or rock planets, are dense. They have metallic cores and rocky mantles and a lower density silicate crust. And so this kind of generally the Earth, the Earth layers with its interior of a solid metal iron core and nickel core, a liquid outer core, a more dense rocky mantle and a less dense rocky crust. Venus is a mimic of that, we think. Maybe the crust is a little thicker. Mercury's got that mostly metallic core, kind of that partially molten, partially solid, and a thick silicate rock crust. And Mars is probably pretty solid with little or no liquid in there. And that's kind of how they differ. But they all have a metallic core and they all have a silicate rock crust. The Jovian planets are bigger, so they have more gravity. They're also farther from the sun, so their atmospheres are thick. A lot of hydrogen and helium in their atmospheres. That fades into liquid hydrogen in Saturn and Jupiter, down to liquid metallic hydrogen with a silicate rock core. Saturn is thought to have a little bit of ice around its silicate rock core. And then there's more ice in Neptune and Uranus. In fact, they're called the ice giants, whereas Saturn and Jupiter would be called the gas giants. Neptune and Uranus are thought to have a larger slushy rocky ice mantle around that silicate core, and then some big, thick atmospheres of gaseous hydrogen. How do we know it's in the planets? Well, there's a few things that we can look at as clues. First off, we know a planet's got liquid inside if it produces a magnetic field or even a weak magnetic field or a fluctuating one. We also know the planet has liquid in its interior if it bulges out at the center. Bulging out the center because of its rotation. So the Earth does this. The Earth is called a oblate spheroid. That means it's a sphere that's flattened out at the poles and bulging at the equator. This is because it's got liquid inside. The planet has this oblateness. We know it's got liquid. What are some other things we can learn about the interior planet? Well, wobbling. We talked about this term earlier, precession, as it alters our view of the stars. Precession is caused because either one, the core is more dense than the outer materials, and we see that a lot in the planets. Depending on how much of wobbling is being done and how it wobbles, we can tell exactly how much different the core is from the exterior. But we can also note that wobbling is caused by internal liquidity. If you take a raw egg and spin it, the liquid inside is going to slosh around and slow down the spin and make it kind of wobble. A hard-boiled egg is going to be different. It's going to spin faster and have less wobble, a different kind of wobble. The Earth has a wobble precession. We noted that it changes our view of the stars. We can also look at mass distribution. When you look at the surface of a planet, either through a spacecraft or telescope pics, through satellites and orbital oscillations, you can actually see differences on the surface of objects. The moon, for example, did you know that the near side of the moon is thinner? Its crust is thinner than the far side of the moon. This is probably caused by the fact that the moon is in tidal lock with the Earth, that it keeps the same face towards the Earth all the time. So it stands to reason that gravitation and rotation and revolution produce this thinner crust on the near side, thicker crust on the far side. Another example, Mars. When looking at Mars through observations that we mentioned above, Mars has a southern highlands that is much taller than its northern volcanic plains, about 4 kilometers taller. So the geographic center of mass is off on Mars. So looking at how mass is distributed and how the planet wobbles, and if it's got kind of that internal liquidity, we can get a sense of what's inside the planet. We can also look at the density of the surface of the planet through observations, the surface material through planetary probes or even orbiting satellites, telescopic views. We can see what materials the surface is made of. We know what density that is. And then by looking at how the planet orbits the sun and how it rotates and how it interacts with any satellites that are orbiting it, we can determine the overall density of the planet and therefore compare the density of the surface with the overall density to get an idea of what the density inside is. One little note there, which we see here, a picture of the surface of Saturn's moon Titan. I just want to pause for a moment and soak this in. You are looking at the surface of a moon millions of miles away from us. From Earth, we built a spacecraft that we launched at a little tiny bright dot in the sky. That spacecraft made it to that dot safely and successfully, orbited around that dot, took pictures, sent it back to us, and launched a probe that went down to an even tinier dot that's orbiting it, safely landed, took pictures, and sent them back to us. That's amazing that human beings could do such an amazing thing. We're capable of lots of great things, ladies and gentlemen. That's awesome. Look at the thing that you're seeing is the surface of another world. That's pretty awesome. Another way we can tell about the planet's interior is by seismic waves. This works for the terrestrial planets, not so much for those gas giant or ice giant planets where the surfaces are primarily liquid. But if you have a solid surface of a planet or a moon, you can detect seismic waves. Seismic waves are the vibrations produced by planet quakes. When rocks in a planet's crust build up elastic energy, the rocks can break and slip to release that elastic energy, and it vibrates through the earth. These are seismic waves. That's what an earthquake is. We call a planet quake here on Earth earthquakes. We call them moonquakes on the moon, and we call them Mars quakes on Mars. But this is simply seismic waves passing through the planet. And seismic waves actually will pass through the planet. They'll go all the way through the planet, and we can actually watch the seismic waves as they vibrate through. And when they hit material of different densities, they slow down or speed up and change direction. So depending on how much they slow down or speed up, we can actually surmise what that layer is made of, what its density is, and what its likely material is. This is how we know what is inside the Earth. You'll see my graph in the lower right. We can see when looking at the seismic waves, they're so-called P waves and S waves. When you look at them, they speed up and slow down when they hit different transitions and layers in the Earth. This is how we know that the Earth has a crust, a mantle, an outer core, and an inner core. We can detect and place seismometers, so-called seismometers. These are devices that detect seismic waves. And we can watch the speed, amplitude, and direction of the seismic waves in planets and moons and determine, therefore, then their interiors. It's analogous to an ultrasound. Like if a pregnant mother goes in and gets an ultrasound, you can see the form of the baby inside, or you can get an ultrasound of a heart when you have heart trouble or something like that. They can do some amazing things with sound waves. Same kind of deal here with seismic waves. And of course, the Earth's interior, crust, mantle, outer core, inner core, know it, love it. You're going to see it on the quiz. This is Earth's interior. Okay. For more details, take natural disasters. And then, of course, we've already discussed the planetary interiors, but just to summarize, through all our knowledge of observations of the surface, orbital observations, magnetic fields, seismometers, we've surmised that the interior planets are something like this. Okay, so also study these, the terrestrial planet and Jovian planet interiors. You'll see these as well. That, ladies and gentlemen, is a look at magnetic fields, planetary interiors, and how we know. Thanks for listening.